to hear what he has to say on protein structure, because he's the protein structure wizard. So I can't wait to hear it.
Can you all hear me? Okay, great. Yeah, thank you for the invitation. So great to be here. It's been a wonderful workshop so far. So I've been giving this talk recently, which is sort of more of a bit of a kind of an overview of the field, I guess. I sort of interleave some of our own work with kind of where things currently stand in the space, particularly given the kind of the rapid pace of change. I think it's always kind of nice to just sort of step back and give more of an overview talk as opposed to kind of deep dive into one particular area. And I figured for this audience, especially, hopefully this will be of interest. So what I'll do actually first is just kind of describe a bit of our OpenFold effort, because I know that's something kind of ongoing, and we're now sort of applying this to the AlphaFold 3 system, which just came out recently. So I'll spend a few slides on that, and then I'll kind of pivot and like I said, sort of give more of a status update on the field as a whole, breaking it down into sort of various components, various sort of applications that people have been trying to do with kind of AlphaFold-based modeling, and then giving a bit of an, like I said, status update on each. So just in case, I know here not everyone is a protein person, so just as a bit of a background, right? There's this competition that happens every 2 years called CASP that's been running for over 20 years, where people assess the quality of protein structure prediction methods, for kind of a blind setting. And what the kind of the context here, right, is that this was going on for, like I said, about 20 odd years, and one measure of accuracy is RMSD, so how far you are from sort of crystallographic structure, right? And for much of those 20 years, the performance was kind of going up and down. There was some obviously trend of improvement, but I would say for much of the 2010s, it was a little bit early 2010s and the 2000s, it was actually a fairly stagnant field, right? There was not a ton of progress, and it was kind of if you were in these meetings as I was, it was a little bit depressing sometimes going to them, and you just feel like not much is really happening. Despite, I will say, some sort of fairly fundamental kind of scientific developments happening under the hood, like, for example, the whole coevolution revolution, that really, I think, significantly moved the needle in terms of what we could do with protein structure prediction, but that hadn't yet kind of quite materialized at the level of CASP, if that makes sense. That really sort of changed with AlphaFold 1 in 2018, right? Where there's a couple of things that they did, I think, but it was mostly, I would say, sort of engineering, good engineering, and that really kind of pushed it down significantly. So as you can see, there's sort of a very big leap in performance, right? It was interesting from a methodological standpoint, but maybe it was less interesting from a kind of biological standpoint, in the sense that the accuracy was still sufficiently poor that people couldn't really do anything with it in terms of like biological discovery. But obviously, the kind of the big news happened with AlphaFold 2 in 2020, where I think both on kind of the science side, they really pushed the envelope. There were a bunch of new ideas that I think weren't necessarily in the ether, or at least maybe they were in the ether, but they were kind of isolated, and they kind of brought them all together. But also more notably, maybe, is the fact that now, right, that the resolution was sufficiently good that you could do, like, you could actually do biological discovery. Right? You could ask questions, you could get insights that these weren't just sort of interesting for method developers. These were interesting for people who are trying to do biology or biochemistry. And this is sort of what it looks like. For the most part, ground truth structure superposed on an AlphaFold 2 prediction looks really good, right? Remarkably good. I mean, I think this was sort of mind-blowing for somebody, I think, even 2 years prior, to think that we can get to this level of accuracy so quickly. Now, for AlphaFold 2, at least DeepMind, I think, was very generous. They released the code from the get-go, including the model weight, so people can make predictions from day one, unlike the current situation with 3. But they did leave out kind of the training component, right? So there wasn't any of the machinery and the framework needed to do training. There wasn't any of the data sets needed to do training, particularly at this, they do this kind of self-distillation procedure, which requires a lot of predictions to be generated from the get-go. And now, with 3, it's even an order of magnitude more, actually. So we thought it would be good to essentially, almost as a principle, show that we could produce a system from scratch, right? We implement it, completely new code base, train it as they did, based on their sort of descriptions in the code in the paper. I mean, and then actually show that you can get to full parity with AlphaFold 2, which we did. And actually the paper was preprinted a couple of years ago now, but it came out just a few weeks ago in Nature Methods. And I think one thing we wanted to do is to really have kind of a platform for building new capabilities, right, to go after new things. And I think that set us well now for OpenFold 3, where we think we could sort of do this pretty quickly and hopefully get to parity with a newer system in a matter of months. Just kind of set the tone, and that this actually does work. So this is a scatter plot, right, of predictions from AlphaFold 2 versus OpenFold. Again, this is a new code base and new model weight, so this was trained from scratch. And you see that it's sort of in aggregate, they're essentially equivalent. On any given prediction, one could do better than the other, but that's both because there's inherent stochasticity in the kind of the input pipeline, as well as the fact that this is a newly trained model, so a new set of weights and so on. But in general, the pink I think is a crystallographic structure, blue is AlphaFold 2, and pink is OpenFold, and they're highly superposed, right? So in general, they basically look the same. We did, I think, do we managed to actually put some improvements in terms of how how well the model works from just kind of a quality of life perspective. So it is actually fair bit faster than DeepMind's JAX-based version, 3 to 4 times faster. Much of that, I will say, comes from help from NVIDIA and Microsoft, who really kind of helped us with the software engineering side of things. And it's much more memory efficient, so we could go up to over 6,000 residues on a single GPU relative to something like 2,400 for the DeepMind implementation. And one thing to note is that these are all code-based improvements. So if you don't want to use our weights, you just want to use the DeepMind weights, you could actually stick them to the PyTorch code base and then just have it run, right? So in that regard, it's actually perfectly compatible. So the weights are interchangeable.
This might be the right time to ask.
Yeah.
So when you say inference on longer chains,
yeah.
Why is that? Is that because
memory improvements?
I'm sorry.
Memory.
Okay.
Memory issues. Yes. You just got out of memory on a single GPU, and this lets you go further. Absolutely. Yeah. Yeah, I mean, the peak memory was reduced by almost like a factor of 10. And AlphaFold 2 is cubic scaling. So 4,000 versus 6,000 is actually a really big difference in terms of memory footprint. Yeah, and like I said, this really, we can't take too much credit for this. It was in collaboration in large part with Microsoft and NVIDIA. Particularly, we sort of built some low memory attention kernels. Essentially, if you think of it as like flash attention 2, but lifted to the kind of the triangular attention, the geometric attention that AlphaFold does. And actually, NVIDIA recently, this is completely independent of our own work, they released a system based on OpenFold that does model parallelism as well, not just data parallelism. And they trained on like 2,000 H100s, which was kind of absurd. So that's on the kind of the inference side. On the training side, we've also kind of introduced a bunch of improvements in terms of essentially, I would like to think of it like democratizing the accessibility of the trainability of the system, right? So you could train it on on FP16, on FP8, so even sort of all the GPUs with FP16, obviously. NVIDIA actually internally, they have it running now with FP4 as well, so really on H100s, so very low precision training, and it seems to be stable. So that's, this is also, again, like quality of life improvements to be able to train this on sort of more heterogeneous clusters and things like that, and through deep speed and PyTorch Lightning as well. Yeah. Okay, so that's sort of my pitch for OpenFold, just to say, I think it's sort of a nice code base. It's a way to build on top of that core functionality. And I'll mention some of the things that have emerged actually since we released it, in various applications. But suffice it to say, for us, free obviously is now the next frontier, and that's what we're working on for the moment. So with that in mind, now let me kind of step back and try to break down the field into kind of 5 main sort of applications, and then just give you a bit of a status update in terms of where the field as a whole stands and some of our own efforts in the space. And like the other speakers, please feel free to stop me so that I don't go over time without answering any questions. So do that whenever you wish. Okay, so some monomers, right? So just to again kind of bring this back, right? So this was the CASP 14 experiment. It was amazing. It was kind of really big story. But I think one question that wasn't maybe entirely obvious, right? Because the intent I think for DeepMind was to develop capability, right? To show that we can actually do this, right? I think that they were maybe less sort of interested in asking, well, how does this system sort of behave under various forms of stress, if you may, which is something we thought would be good to do. So one question, and this is some of the OpenFold work, was to essentially assess the ability of the system to generalize to sort of unseen regions of structure space, right? In their case, they trained it on the PDB, and really the only sort of true assessment was on CASP 14, which is very hard, I should say. I think that's as good as it gets. But it did leave open the question of, well, how does this do if we are sort of assessing it in sort of new unseen regions of structure space? So the first thing we did, right, was to say, oh, well, what would happen if you just simply take the PDB and sort of reduce it, right? So if you just had less data, right? And so this is kind of a random reduction, right, where you're essentially taking smaller and smaller percentages of the PDB, right? So at 100%, it's about 200, well, depends on how you count, but let's say about 200,000 chains. And then all the way down here is, on the order of maybe 2,000 chains, 2,000 unique protein chains, essentially. And these are just training curves, right? So LDT is one metric, one is really good, 0 is bad, and this is as a function of training time. So so what's interesting, with pink, this is not a fully trained model, I should say. This is only about maybe 5% of training time. So we would normally train it for much, much longer. But each of these curves is like $50,000 of GPU time. So we can't do this too many times. So we only do sort of early training. Yeah.
One very basic question. Sorry if I missed it. Like in this model, what's the input and what's the task? Just to be sure.
Oh yes. Sorry, maybe I should be. All right. So this is sort of the protein structure prediction problem, right? So really, well, all right. So kind of aspirationally, the problem is given a sequence, a protein sequence, predict the structure. Often the structures corresponding to something like lowest energy, sort of state in the kind of conformational ensemble. Of course, there's artifacts coming from crystallization conditions and so on. So the ground truth data here is coming from typically crystallization, maybe some cryo-EM and NMR. And so those experimental methods have their own issues, obviously, and that's going to kind of percolate into the data. But that's the task.
It's like the protein sequence as input.
Right.
Is it some form of text or is it a graph?
Proteins are polymers, so it's just a sentence, it's just a linear text.
Okay, and you try to predict a graph, which is like the structure.
You really try to predict the atomic coordinates, so it's XYZ of the atoms, and you try to do that at the level of like each individual atom, including the side chains and so on. One note that I'll come back to this, and it's actually somewhat subtle, but it's not, is it's not really a sequence to structure method. I will say AlphaFold too. It's more what I call a multiple sequence alignment to structure method, or an MSA to structure method, because you don't just use a single sequence. You actually use a sort of set of homologous sequences. So sequences that have evolved to sort of essentially have the same structure, and all of those go into the prediction task, and that's actually fairly critical, as I'll talk about later on. So there isn't really yet a sequence to structure model, I would say. That's certainly as performant as AlphaFold 2 is. Any other questions? Yeah, thanks for the clarification. Right, so coming back to this, right? So the kind of the pink partially trained model, right, is here, right? And certainly if you reduce it all the way down to like 2,000 structures, you do see something of a hit, right? But even the sort of the teal colored curve, right? This one here. Is reaching a PLDT or an LDT out of about 0.7, 0.72, which is actually pretty good, right? And the reason why I say that is because if you even look at the first AlphaFold, right, the one that I said made a splash in 2018, that AlphaFold, right, was had sort of a mean LDT of 0.6 on CASP 13 at the time, right? So this model is actually better than that first AlphaFold, right? And I often belabor this point because I think it's really, really interesting. Right? But the fact that we have a model that's able to outperform another one, even though it's trained on 100 times less data, right? Because the first AlphaFold was trained on the whole PDB, right? Is a sort of testament to the value of sort of architecture engineering, right? That having a good model that's really sort of incorporates the right priors and that's able to sort of leverage as much of the data as possible can make you 100 times more data efficient in this context, right? And that's really non-trivial, right? So that's sort of encouraging and suggests that the model, that maybe we don't need as much data as we thought we did to be able to do this. One wrinkle I should say, I mean, so this is sort of interesting in the sense that, could we have done this with like the PDB of 20 years ago? And maybe we could have, right? But the one wrinkle here is back to the MSA question, or the MSA point, is that much of the growth in data that's happened over the last couple of decades has actually come on the sequence side, right? Where we have many, many homologous sequences to any given protein of interest. And that's permitted us, right, to build these deep multiple sequence alignments that allow a model like AlphaFold 2 to do well. So it's not just about structure; it's also about sequence, and that's a little bit sort of maybe lost in the conversation. Okay, but on this front, right, this is all just purely random splitting, right? So there's not actually real generalization to sort of new regions of structure space. But we can do that. Right? There are many classifications that essentially kind of take structure space and sort of decompose it into clusters, right? Into a hierarchical sort of clustering scheme. And then you can ask, if I sort of train on sort of one branch of that structural classification, how well do I do to other branches, right? And we can do this sort of the level of topology, which is maybe like 100 different classes for the whole PDB, all the way up to the level of class, which essentially splits all the PDB into like 4 major classes, right? Along the lines of whether they're alpha helical or beta sheets or combinations of both. So this is a much more stringent test of sort of generalizability, right? And what's interesting, and so now the percentage here corresponds to the percent of classes, right, to the fraction of classes that are retained for training versus ones that are being used for testing. So when we say 5%, this means only 5% of the topologies in CASP are being used to train, and then the rest are being used for assessment, right? So similar to the previous case, right, you do see a bit of a dip, right? But what's interesting, again, at 10%, so this is now structurally stratified 10%, we see a model that's more performant than the first AlphaFold, right? And this holds for classes, for architectures, and remarkably even for classes, right? So in this case, these are models that are essentially trained on largely alpha helical proteins and tested on beta sheet proteins, and vice versa. And again, the model is actually performing at the level of the first AlphaFold. And just sort of visually to sort of communicate this, on the top row, right, is a model that's trained on alpha helical proteins. And the targets are the ones in orange. So that's what we're trying to predict, right? So the magenta is a model trained on alpha helical proteins. Sorry, I misspoke. So back up. So the top row is the prediction target is the alpha helical protein in orange. The magenta is a model trained on alpha helical proteins being tested or assessed on that protein. And as you can see, it does pretty well. But the green is a model trained on beta sheet containing proteins, and it's being tested on that same protein, right? And here you see it sort of hallucinates a beta strand. And then conversely, on the bottom row, we see a target that's dominated by beta sheets. And what's interesting here is that the magenta, right, so this guy, which is only seen alpha helices, doesn't recover the kind of the right hydrogen bonding network that allows sort of pi-mol to see sheets anymore. So that's all gone. But nonetheless, the C alpha trace is pretty good, right? So it's actually able to place the atoms of the backbone in roughly the same place. Right? So it gets the overall geometry right.
Or just like there's not.
It's like 1% of the
Like it does see a tiny.
It does see a little tiny bit. Yes. Tiny little fragments here and there. Yeah.
Yeah, it's a related question for the drawing software, for example. What is the tolerance for whether or not it gets drawn as a beta sheet? Is it an issue of the angle? Is it an issue of
well, for beta sheets, also the hydrogen bonding networks. I don't know exactly. I mean, it's probably 0.1, 0.2 angstrom, something like that. Don't quote me on the precision.
Tolerance, it needs to be accurate in order for it to be.
Yeah. So it needs to be pretty on point. That's my guess. Don't quote me, but I'm guessing it's on that range. Yeah. Yes, absolutely. And it's the sort of thing which I wouldn't be surprised if you feed this to like a physics-based relaxation, you may actually recover it. It's quite possible. Yeah. Absolutely. Now, so on the one hand, this seems kind of like a miracle, right? Because you're sort of generalizing in a way that like no other machine learning model generalizes, which seems like how the hell does this happen, right? I do think what's really happening here, and this kind of goes back to the question that was asked in the beginning, that this is an MSA to structure predictor, right? And so really the generalization task is, right, can you essentially read an MSA? Can you look at this sort of object and identify patterns of coevolution that tell you sort of these sort of kind of patterns of coupling that can then be converted into essentially Cartesian constraints, right, on the geometry. So in that regard, right, in a way, this is maybe not as as difficult a generalization task as it may seem, right? Because you do have all that information there, and it's just about being able to translate it into a 3D structure. Yeah.
So I'm really ignorant about the architecture of these approaches. Is in AlphaFold and in OpenFold, is after you make that initial prediction, is there some downstream optimization that takes that as input and does something else with it before you produce a final output?
Generally, no. This is a fully end-to-end system. I mean, they do if you sort of want to. There's a bit of a physics-based relaxation that you could perform, but it's sort of super marginal. I mean, you can certainly leave it at. It's not critical.
Okay, so your comment about the multiple sequence alignment and finding it's really just predicting that geometry.
Yeah, that's right. And that is sort of a general purpose thing that's universal across all protein folds. And essentially, you don't need to learn it in a fold specific way.
Have you tried testing this hypothesis about generalization? Say, like making a synthetic POTS model generated MSA and see if it folds it?
So Sergey Ovchinnikov did something kind of like what you're saying, which was a bit of an adversarial example, but I think kind of shows this point, which was to essentially reverse the sequence, right? Reverse the just the ordering. But retain all the coevolution pattern, and sure enough, it gives you a protein that satisfies all these. So obviously, it's not doing something physical at that point because that protein will not fold, right? But it's folded it. So yes, yeah.
I guess just related to that, could you also just give it the sequence without the MSA, like just pretend that the MSA didn't exist, and then would all these generalizations go away?
So in general, the system just fails when you do that anyway, right? It doesn't really work. The only case where it does work is often for de novo designed proteins, and the kind of the theory is that because they're so optimized for like rigidity, that's able to kind of still identify the patterns. But that sort of thing just kind of breaks the system in general anyway. So yeah.
can I ask another question about this sort of structure prediction problem? So I could imagine when you ultimately predict the 3D structure, there can be sort of small perturbations that basically are energetically equivalent, right? I mean, rotations of the whole molecule, or maybe small stretches.
Sure.
Is that actually at all taken into account, or is it?
So this system AF2 was a SEC equivariant, right? So it is equivariant with respect to translations and rotations. The new one, ironically, isn't. So on that front, at least. Now, in terms of, I mean, so it's not an ensemble predictor. So if you're asking about sort of iso-energetic sort of, conformations that does it give you something like an ensemble that, of all of them? Not really, right? It's
I mean,
people have poked it.
There's not only exact symmetries, right?
Yeah.
If I just stretch it a tiny bit.
Sure.
It might look completely different, but it's energetically almost in the same configuration. So
Right. So
all taken into account in these.
no, not really. People have tried to poke it in various ways to get it to do some of this stuff, and I'll talk about that later on. But for the most part, it doesn't. Basically, is what I would say. Yeah.
Okay.
All right, so that's it for monomers. Now let me get this second piece, which is mutations, and this kind of gets back to this question of MSAs actually. So it's sort of it kind of comes back full circle in a way. So I will say, sort of interesting. I think I'm going to alternate between areas where there's been a lot of progress and where things are working well, and areas where there's not been, and sort of it's a bit stuck. And I think mutations is one of those where it's a bit stuck. So the TLDR doesn't really work, and I think part of the reason is because of this question of the MSAs, right? So in a way, you could think of MSAs as sort of averaging out sequence variation, right? And what I mean by this is in a specific sense is that what you essentially ask in the model is to say, okay, you have all this variation in sequence, which might come with some variation in structure. But what I want, right, is essentially to kind of almost orthogonalize with respect to that variation. Tell me what is common, what is universal and constant across all this variation, and that is the piece that I can reliably predict into the structure, right? In this context, where, just to be clear, maybe I should have given some motivation for what I'm talking about here. So for mutations, what I mean is, can we predict the impact of structurally perturbing mutations on the structure, right? So if you have a mutant protein sequence that's mutated in one residue or more residues, and somehow that changes the structure in a kind of in a predictable way, right? So it doesn't just completely unfold the protein, but it does something kind of interesting, right? Can we predict that, right? That's the question. That's what's interesting in this context. The issue, right, is that this is almost adversarial to this kind of setup, right? Because alpha is almost incentivized to learn to ignore these types of variations, and this is the kind of thing that we're interested in here. So it's really not particularly well suited for this problem, right? And AlphaFold doesn't change anything. Now, people, I think ourselves included, we're sort of hoping that protein language models would really make a big difference in this context. And the short answer is that they haven't. But let me just kind of walk through a little bit of what we've seen so far on this front. So if you don't know what protein language models are, I should just say, so these are essentially, so GPT-like architectures applied to protein sequence databases instead of natural language databases, right? They're typically not autoregressive. They're typically MLM-based. But the basic premise is you're doing some sort of self-supervised task on protein sequences, and the hope there is that you sort of induce sort of general understanding of protein sequence space, right? And then that will sort of help you to, for this case, be able to predict structures without having to go through the MSA kind of procedure. And it does, but it doesn't really address the question of mutations. Yeah.
I like this point, but I guess I'm wondering, like the coevolution methods.
Yeah.
Argue are actually really good at using the evolutionary information to predict mutations. So it seems like it could potentially not average out the sequence variation and pick up on important, at least coevolutionarily disrupting mutations, right?
So I think there's two things going on here, right? And you see that even with the protein language models. So the protein language models are actually really good, essentially variant effect predictors, right? I mean, good in the sense that they're as good as we have right now, right? So in that regard, you're absolutely right. They are learning something about sort of favorability and so on, right? And I could even imagine a version of AlphaFold which sort of learns to say, this protein won't fold. This is it's not thermostable anymore, and I just kind of give up, right? I think that's perfectly plausible. The issue here, though, right, is this, right? Is that we are trying to capture the effect of those mutations on structure in a kind of a controlled manner, right? So if there's like a domain shift that occurs, right? Like in a kinase situation, right? Where the DFG loop sort of changes, right? So in those cases, we just don't have the data. That's the issue, right? So it's a supervised problem that we don't really have enough data for to be able to train this kind of model. Yeah. Right. So I think that the kind of the most famous of these kind of models is the ESMFold. There was a parallel model called OmegaFold that did something very similar. But in the ESMFold case, what they did basically was they trained this kind of large protein language model called ESM2, and then they fused it to OpenFold. So essentially, remove the MSA component, and then just have the folding kind of structure module from OpenFold kind of be on top, and then just predict the whole thing end to end. So essentially, what this ends up doing is sort of maybe implicitly trying to extract coevolutionary information from the PLMs, right? And that seems to be what happens. So what's nice about this approach is that it's very fast, because it eliminates the MSA construction step, which is actually very compute intensive. And so they were able to apply it with kind of metascale resources to hundreds of millions of predicted protein structures or protein sequences, right? So that was kind of nice. But when it came to the question of the mutations issue, it didn't really work, right? So this was CASP 15. This was the experiment that happened 2 years ago. It's a bit busy, so let me walk you through it. So the x-axis here is essentially a measure of how deep the MSA of a sequence is. So the leftmost predictions are ones that have very deep MSAs, and the rightmost ones have very shallow MSAs. And so what we see, right, is and again here, high is good, low is bad. And red are the protein language model-based methods, and blue are the coevolution explicit MSA-based methods. And so what you see is that for deep MSAs, not surprisingly, everybody does well and everybody's happy, right? But for this region, for the low MSA region, both sets of methods kind of degrade, right? But the red ones, the ones that are language model-based, they do actually worse, right? And this should at least surprise you a little bit, right? For at least because MSAs don't even factor into the prediction process and doing inference time, right? The predictions are being made from individual sequences. They're not actually you're not feeding the MSAs in them anymore. But right, what this is saying is that the corresponding region of sequence space, right, is shallow, is sparse, because the MSAs are shallow, right? The protein language models seem to really struggle in being able to give sort of useful signal for the structure prediction method to proceed, right? So that's what's really happening. I mean, that's at least I think the view currently of what's happening, right? So that in a way, I mean, this is sort of a bit of a negative result, yeah, because it's saying that maybe we're not really learning, sort of properties of sequence structure inherent to like the sequence itself. Instead, we're really learning a set of coevolutionary patterns, and that's what the PLM is learning, just kind of memorizing those results, right? If you talk to Alex Reeves, who's sort of leading the evolutionary scale team now, kind of pushing this on further, I think what he would say is that this is just a function of like how far down you go in the complexity curve, right? So if you keep scaling up, right, you're going to keep pushing the model toward lower complexities, and eventually all the coevolution stuff will be extracted, and then it has to learn something different, and that may well happen, right? But I think so far that hasn't yet quite happened, at least from what we can tell. So just a bit of a kind of a side vignette. So there's this really, I think, beautiful work by Sergei Ovchennikov's lab that got at this question of, does the model learn any kind of implicit physics, or is it actually just coevolution, kind of like what we've been saying so far? So in particular, the hypothesis here, right, is that maybe what the MSA does is essentially give you kind of a good guess of where you need to be in the energy landscape, right? So it kind of sculpts your landscape. But then to get to the lowest energy, right, to actually get the right conformation with all the little details right and all the sidechain atoms in the correct place and so on, it sort of needs a kind of an implicit physics function that it's learned through the process of supervision to get it down to that valley, right? So there's a kind of a duality to the way the system works, right? This is at this point just a hypothesis. But they test it in this sort of really nice way, where what they essentially do, a bit of like so the question that came up earlier, they remove the MSA from the inputs now. They just give it a single sequence. But because the model sort of would generally fail in that context, what they additionally do is provide a template in the form of a homologous structure, or not particularly homologous structure. So just to be clear, as one of the inputs to AlphaFold, you can actually provide kind of a structural hypothesis. You could tell it, this is what I think the structure ought to look like, right? And in this case, what they do, right, is they provide essentially 100 different structures, right, of varying homology to the structure of interest. And then they ask, how well does that correlate with this sort of notion of a composite score that basically kind of summarizes how happy AlphaFold is with that structure for the given sequence, right? And this is what the scatter plot is showing, guys. So the TM score here is basically how close is the template, is the structural hypothesis, right, to the structure of interest. And the y-axis is how happy is AlphaFold with that hypothesis. And what you see is that there's a pretty decent correlation across all those structures, right? So it seems to know how to rank structures. It seems to know, even without an MSA, right? So here, this is missing an MSA, right? Which is purely based on sequence, right? And the structural template. It knows how to essentially weigh relative structures and figure out which one is better, right? So this is quite important, right? It seems to have learned an implicit physics function, in addition to whatever else is learned, right? But probably what's happening, right, is that, this kind of goes back to essentially what becomes like a sampling question, right? Is if you are not constrained in any way, if you don't have an MSA, so you're not being placed in the right region of sort of conformation space, then the search space is so large that it's very hard for the model to implicitly fold the protein, right? It's simply not trained to do it that way, right? So instead, right, it sort of just fails. But if you provide it with that hypothesis, then it's able to actually rank, and that's I think what we're seeing here. So going back to this question of training and so on. So we were actually interested. I will say this was actually triggered by reviewer comments. So this is one time where reviewing really helped. So we were interested in asking. Well, one question we were interested in asking in general was, what is the convergence behavior of the model? Because that's not something that DeepMind reported on for AlphaFold 2. So in particular, what we see, right, is the model seems to achieve essentially, a fairly well, this isn't say the final level of accuracy, but it seems to achieve a fairly large fraction of that final accuracy within a few days of training, within about 10% of the full training time. So it gets there pretty quickly, right? So that was sort of interesting for various reasons. But then we wanted to ask the question: how well does this map to this kind of knowledge of implicit physics, right? Like, does it learn to interpret MSAs before the physics, or how does that work? And the question. The answer, rather, so it seems like it actually learns the implicit physics way later, right? So what we see here as a function of training time is essentially the correlation, right, of this sort of AF2 rank experiment, essentially. So we're asking how good is the kind of implicit physics function as a function of training step. And what you see that for up to like 12,000 steps, right, so I know I'm scrolling back and forth, but that's where, where we're here, right? So the model is pretty performant in sort of absolute terms, right? This is a pretty good model at this point already. But the physics function, that sucks. Right? Well, not sucks, but the correlation is quite cool, right? Relative to where it eventually gets to, right? So this kind of long tail of training, which consumes like 95% of the training time, is largely actually spent, it seems, for it does several things, but one of the things it does, it seems to learn this implicit physics function. So that's quite interesting, right? Is that this seems to come much later than the kind of the MSA piece, which is learned pretty quickly. And incidentally, just more parenthetical point. So one of the things that AlphaFold does is cycling, where it sort of takes a structure and feeds it back into itself and kind of repeats it over and over again. What you see is that when you have a deep MSA, it sort of pins down the structure very quickly, right? While when you don't have a deep MSA, just even a shallow MSA, it often takes many recycles to finally fold the protein. So even then, you begin to see this sort of implicit sampling kind of procedure in the system.
Sorry, no, ESMFold, sorry.
Yeah.
It does.
Yeah, they're architecturally essentially identical. Yeah. ESMFold doesn't take templates, however. That's one thing that it doesn't do. And I'll actually, that's the next slide. So one thing we did, actually, this is not published work. It's sort of something we put up on GitHub. You can download it, but we don't quite know what to do with it. So it's just kind of there for us as code right now. Is a sort of solo-seq model, which is very similar to ESMFold. But the difference with it is that it actually lets you put in templates. So you could do this kind of experiment where you inject the structure and ask how well does it do. And what's interesting is that for the AF2 rank application, right? So yeah, so essentially, same thing as before, but remove the MSA and put a protein language model. What we see here for CASP 15 targets is something somewhat interesting. So solo-seq on its own is not very good on these very difficult targets. But what's interesting is that when you do provide a template, so you're giving it this kind of structural hypothesis, and then you ask how well correlated is it with the decoys, it actually outperforms both ESMFold and AlphaFold 2. Right? So this sort of approach, which is a sort of protein language model-based approach, seems to actually learn a better physics function than the MSA-based approach. Now, there's no reason to think that ESMFold would do even better. The only reason we can't do that experiment is because ESMFold doesn't have a template module, so you can't give that information to it. But OpenFold solo-seq does, and so we could do that. So as far as sort of a ranking function, this I think is probably state of the art right now in terms of ranking functions. I mean, modular AlphaFold 3. Yeah, and it's available if you just want to play with it. If you're interested, just a bit of a pitch.
You can just give it one template, or you can give it.
You can give it 4. Yeah, you can give it 4. But I mean, you can do this in a kind of autoregressive way as well if you really wanted, right? So there's all sorts of ways you could do that.
Okay.
I think I'm doing okay. So now let me kind of pivot to multimers and complex. So unlike mutations, this is, I think, one area where we've seen amazing progress. Really, it's just kind of mind blowing to me. I think how quickly this has moved, and I don't know if people fully understand the implications of where we are in this space. It feels like there's some kind of profound shifts that are in place. So all right, so let me kind of break this down in various ways. So going back to CASPs, right? One way, so sorry, let me just back forward. So the question here is complexes. Right? So we're asking, how good do we predict complexes, not monomers anymore, right? And in particular, what we're going to focus on are these sort of ICS scores, so like the interfacial contact scores. So essentially, how good is the interface being recovered, right? So if you look back at the kind of pre-CASP 14, red is basically bad, right? So this is kind of the various ranges of accuracy. So below 0.5 is a fairly poor prediction. Blue is sort of a reasonable prediction, and then green are like the ones that you really want, right? The good predictions. So CASP 12 and 13, not surprisingly, things were not doing very well. Even at 14, where AlphaFold 2 debuted, because it wasn't really kind of being, it wasn't being used for complexes, it wasn't being kind of assessed properly, it wasn't trained properly for that purpose, it was still the case that most predictions were poor. But at CASP 15, that what happened 2 years ago now, the performance really went up, right? So green is more than half now, and blue is something like, the remaining 30%. There's maybe like 15% where the results are still poor, right? So just to kind of pause for a moment, right? This has fairly profound implications, right? This is what this is saying, is that at least for, well-ordered, fairly stable complexes, and not kind of these sort of highly transient, very weak interactions, but like for stable, complexes, right? For dimers at least, you're essentially getting pretty decent contact for like 90% of cases, right? That's a pretty surprising thing. And these are for CASP 15, so these are really novel, never been seen kind of interfaces. Right? This is not a trivial kind of problem, right? What is hiding in this is so let me just kind of finish the results for you. So here, if you look at the kind of the beige circles, those were the AlphaFold 2 multimer kind of vanilla predictions, and then all the arrows are the best prediction at CASP 15. And so as you see, again, there's substantial gains over even AlphaFold 2 multimer, right? And that's maybe something that's maybe missing a little bit in the conversation, that people don't realize how much better than vanilla multimer that one can do with these sort of approaches. And what is the secret sauce? There really isn't one. I mean, the biggest thing, I think, and that's what's driven a lot of this, is what Warner did, which is basically to essentially turn AlphaFold 2 into like a sampling system, okay? So what he did was to inject noise through dropout during the inference procedure, just to kind of, to make the process even more stochastic. And that allows one to sample enough structures, and because the scoring function is pretty decent, rank order them to then recover the best one, right? So the issue is so on the one hand, this is super exciting. On the other hand, the problem with this sort of approach, right, is that he had to, in some cases, spend like 50,000 GPU hours on a single complex, right? That's super expensive. So you certainly can't do this for like the human, interactome or something. But in principle, if you had some way of actually sort of prioritizing and going after high-value targets, this would let you do this. This would, in principle, kind of let you recover the interactome of a system, at least a stable interactome, let's say, of an organism, which is again a very non-trivial fact. And I'm almost surprised this hasn't sort of already happened. But I think the compute costs are formidable, and that's maybe one of the reasons. Now, interesting to bring AlphaFold 3 into this picture, because I think here we have seen some movement, right? So not on speed, but on other things. So monomers and sort of protein-protein complexes, you do see an improvement, right? It's not trivial. So but again, see how high it is. I mean, this is really remarkable. Where we were really stuck with antibodies, and this is actually where AlphaFold 3 really does seem to make a big difference as well. And what's interesting is you see this particularly in this kind of sampling context, where again, if you make many predictions and then ask how good is the best prediction based on its own ranking function. And what you see that for antibodies, right, 2 is the dark blue and 3 is the kind of light blue, is that 2 used to kind of saturate. Right? It wasn't able to sort of, the sampling wasn't giving you anything, basically. But with 3, you actually see these gains, right? That seem to continue to go on just with more and more samples. And again, the sampling gets pretty expensive, but it seems to get better and better, right? So this is suggesting that whatever sort of implicit physics function AlphaFold has learned is even better, right? Because with antibodies, you don't have any evolutionary signal. So clearly, this has gotten better, but the compute costs have gotten even worse. And so it's, so not sure that's a net win. But it's really exciting that we have this sort of technology, and in a way, all we need to do is speed it up to be able to apply this at scale to recover sort of complexes, at least the dimers, like I said. Okay, so all right, so I think I can wrap up pretty quickly with conformations and small molecules. So Yeah, so it's a confirmation. So with AlphaFold, we're focused obviously on these sort of stable, in some cases ultra-stable conformations that we often get from crystallographic studies. But we know that's not how proteins work, right? Proteins form ensembles and they're flexible and so on. There are, I guess, different definitions of what one would want from this. But at least one possible thing that one would want is something like the major modes of the conformational ensemble. Right? So if you know that there is some non-trivial probability mass associated with certain conformations, maybe you want to be able to recover these, right? And maybe even more ideally, it has something like a Boltzmann weighted distribution, so you actually know the associated probabilities, so the occupancy states associated with each of those conformations in the kind of the best case. So I will say this is kind of back to the more negative space. We haven't really seen a ton of progress. Early on, there were ideas on essentially taking the multiple sequence alignments and introducing various perturbations to get them to sort of flip, to get a protein to flip conformation. So this is one instance where what they did basically was like an alanine scanning experiment across all the sequences in MSA. So convert a residue to alanine, and then see if you can kind of get it to flip, right? In those cases, they already had a pretty good hypothesis as to whether they need to mutate, right? So it's a bit of a catch-22 situation, because if you sort of already know the conformation you're trying to steer it to, is that really a discovery tool? I think a sort of more principled approach came out from Dorothy Kern's group, where what they did was to take the MSA and essentially cluster it based on phylogeny, right? So kind of try to map out sequence variation in sort of in a kind of a more localized fashion, right, across an evolutionary space. And then say, okay, well, if you were to take one particular cluster and feed that into the prediction procedure, what sort of confirmation do we get? And do we get a different confirmation if we use a different cluster, right? And in those cases, for some instances at least, they were able to get, particularly for these like false switching proteins, they were able to get alternate confirmations. But here too, I would say, I think it's a bit anecdotal. I think it works in some cases, but it doesn't work in many other cases. More recently, there's been a couple of papers, one from the Microsoft AI for Science group called Distributional Graph Former, another one from Regina Bosley's group called AlphaFlow, where I'll talk about this one. The basic idea here is actually, I will say, this anticipates AlphaFold 3 surprisingly well, right? So the basic idea here, what they do is they essentially, actually maybe I'll use this sticker, I think it's a little bit easier to show. So what they essentially do is they use AlphaFold 2 architecture to generate representations, right? The latent representations for the kind of the pair and the single sequence representations. And they use this as conditioning sort of variables for a diffusion process, right? And depending on the system, they either train on just PDB ensembles, right? So conformations coming for a given protein, but from the PDB, or on MD data, on molecular dynamics data. And that's what they try to do. And then they assess how well they do in terms of recovering kind of the conformations, or in terms of being able to actually provide something like Boltzmann weighted probability. So in this case, at least for the PDB, so I will say I think the MD results are actually kind of exciting and pretty promising. The PDB stuff, though, I think still is nascent. So in this case, what I'm showing is the right one is actually the more relevant one, is essentially a precision recall curve, right? So you want to be as precise as possible and have as high recall as possible. AlphaFold is a green dot, and that's maybe part of the problem already, right? Is that you see this is almost nearly the best model. If you do the MSA subsampling thing, the one I talked about earlier, you can kind of scan the space. But the thing is, you don't necessarily get higher precision recall than what AlphaFold gives you anyway. And then AlphaFlow, the system with the diffusion stuff, again, it's sort of strictly speaking just kind of worse than what AlphaFold does on its own. Now, it does generate greater diversity, right? So if you look at the diversity metric, these are all much higher than AlphaFold is. So AlphaFold is not particularly diverse. But the fact that the recall is not changed means that diversity is essentially not corresponding to kind of physical diversity, at least insofar as we see it in the PDB anyway, right? So if the PDB is capturing kind of real biophysical diversity, then that's not what's being captured by these models, at least so far, right? But I will say, I think for the MD stuff, it's actually pretty promising. I'm not sure the MD results, but they do seem to learn something non-trivial in the sense that they're able to kind of train on certain classes of proteins and then generalize to other classes of proteins up to the timescales used for generating the MD trajectories. So at least in that kind of limited context, they seem to show some generalization. All right. So in the last maybe 5-10 minutes, I'll talk about small molecule ligands, which actually has been kind of the one that maybe seen the most effort. And I think it's certainly with AlphaFold 3 is started to pay some dividends now. So this I say, I mean, this field goes back a long time, right? This is one of the kind of the earliest applications of like computer aided design or drug discovery, whatever, in this field. And farmers have been working on this for like 20, 30 years, right? So it's a very, very old problem. And the question here is, can we predict? Well, there are many versions of this question, but the question I'm going to focus on is, can we predict the complex of a protein bound to a small molecule? Can we cover the structure of that complex? And you may already kind of begin to see variations of this question. So for instance, what is the input? Is it just a protein sequence and the chemical compound? Are you providing it a structure of the protein? Is that structure in the right conformation that is bound to the small molecule? Right? So there's sort of gradations to this question. And I'll sort of walk through them in a bit. So I'm going to essentially ignore this very sort of venerated history of this field and just jump to like the last couple of years where deep learning really has come into play. Right? Although I'll come back to the classical methods in terms of assessments. So I think the first kind of modern method I would say is sort of diffdoc, again from Regina Batz's and Tom Yaklav's group at MIT. And what they did here was hold the protein rigid. So you are giving the protein structure, and you start doing a diffusion in sort of conformation space and position space over the small molecule ligand. What's interesting about this approach and many other approaches is that they do often lead to sort of non-physical structures. So they're often sort of they often result in chemical compounds that have such non-physical bonds, non-physical angles, things of that sort. And this was sort of really nicely kind of assessed by work from Charlotte Dean's group, where let's see, let me kind of walk you through it for a second. So let's start with the very leftmost set of bars. So those are actually the classical methods. I said I'm not going to talk about how they work, but these are still in a way some of the best methods out there, and they use essentially kind of a physics-based scoring function to dock a compound. So what you're looking at here is two different data sets. Let's actually look at the orange one or the pink one, because that's a sort of more rigorously kind of partition data set. Called this is the one that's introduced in this paper called Postbusters. And what you're looking at is essentially the bar, the height of the bar is a fraction of predictions that are within, I think, 2 angstroms here of or 3 maybe, of the protein small molecule compound, right? So the bar is high, right? You want to get the compound in the right location of the protein, and you want to get the atoms in the right respective location. So you really want to cover the pocket, right? So in general, right? Oh, so actually, one critical point. So for these methods, the classical ones here, what this is being reported on is where you give the whole form of the structure. So you give the structure of the protein in the conformation that is actually bound by the ligand, right? And oftentimes you may not have that, right? Because because if that protein has never been liganded and certainly hasn't been liganded with the one with the molecule that you care about, it may not adopt the conformation that it will adopt when it binds that ligand. So this is a little bit cheating, right? Because you're sort of giving it the answer in terms of what the protein ought to look like. In all those cases, actually, in all those, in the assessments I'm showing here, this is the standard. So for the classical approaches, that we're talking about north of 50%, just north of 50%, in terms of the fraction of predictions that are actually within that kind of 3 angstrom threshold. What's interesting, right, is that if you look, for example, at diffdoc, all the other methods, I don't mean to pick on diffdoc, all the kind of deep learning-based methods, right? They sort of ostensibly seem to do quite well, particularly for all the less well-separated training test set. But if you then control for chemical validity, these drop considerably, right? And that's what the kind of the dash versus solid bars are showing, right? So the solid is the chemically valid subset, and then the dash is the sort of the chemically invalid subset, right? So what this is saying basically is that sort of within 3 angstroms of the pocket, but the geometry is not physical, right? So it's the molecule is being distorted in various ways to give you those numbers, right? There's another way of looking at this, which is to say, what if we break this down by homology by sequence identity to the protein target? So what if we actually assess generalization to new proteins? And here again, you see a similar pattern where the deep learning-based methods do considerably worse when you present them with more difficult protein targets, while as the kind of classical approaches sort of don't really seem to care very much, right? So both of those are sort of indications maybe of some pathologies or overfitting in these sort of methods. I will say for the issue of chemical validity, it can be recovered with physics-based relaxation, right? And this is what that's showing us. So this is kind of essentially here the red and the purple are before and after relaxation. So you definitely, you can recover a lot of it, right? To be sure. But again, you don't quite hit the same rates as the classical-based approaches. So that's where things were, up to a few months ago. Revolutionized all Atom came out, and I think, really push the envelope in a meaningful way. In particular, even though from this picture it looks like it's not doing as well as the classical approaches, that's RFAA, the Revolutionized all Atom, but what's notable here, right, is that this is now trying to do the problem of predicting, of co-folding the protein along with a small molecule. So in this context, right, just RFAA, not the rest, just RFAA is actually solving a more challenging task because it's only given the protein sequence and the small molecule, and it's covering the whole complex, right? So it's having to figure out the conformation of the protein bound to the ligand. Then of course AlphaFold 3 came out just a few weeks ago now, and it's even better, right? It's actually considerably sort of higher than even representative all atom. Again, orthodox Vino is a bit misleading here because this is seeing the hollow form, right? The one that's bound to the protein. But if you look at the, and if you, I'm not showing it here, unfortunately, but actually if you take orthodox Vina and dock it into an AlphaFold 2 predicted structure, so the April form, you'd be like way down here, right? So this is actually a rather considerable gain. I mean, I don't think people maybe fully appreciate how much of a gain it is over what the state of the art is. I mean, for this kind of much more difficult task, assuming it holds in terms of generalizing to unseen regions of protein space, is actually a rather substantial gain. All right, so maybe I'll just say one last thing and then I'll stop. So people ask about what's new with AlphaFold 3, and let me just, there's a bunch of new things that are new. I'll focus on one. So yeah, I'll just skip because I want to give some time for questions. So the one key thing with 2, right, is that it was all sort of residue based. So it only understood proteins as essentially collections of residues. And this was actually, in a way, carried forward in AlphaFold all atom, right? In the sense that proteins were residues, small molecules were atomized, and then nucleic acids were also sort of base-based, right? So each nucleotide had its own sort of representation, but it was not atomistic. On occasion, AlphaFold introduces this sort of atomization step where they take one residue and they sort of atomize it. But in general, it really was just operating at the level of the sort of tokenized residue-based representation. What AlphaFold 3 does instead is basically operate in this sort of hybrid space that's ping-ponging between the sort of residue-based tokenized representation and a fully atomized representation. And I think that's probably the biggest thing, the most important aspect of it. The issue, of course, is that if you're operating on atoms and if you have a cubic scaling system, and we're not going to be happy, right? Because we're talking about the 1000x at least increase in compute cost. So what they do instead is this sort of funky thing where they start out with a residue-based representation. They go down to this sort of so they kind of flatten the structure to a list of atoms, and then they divide it into chunks of 32 atoms each, where the attention is happening to 128 nearest neighbors in the chain, right? In the sort of linear ordering. So what's basically happening is that you take this kind of what is ostensibly, So you take what's ostensibly kind of a global attention mechanism happening at the residue level. You sort of move to an atomized representation, but then the attention is localized in this sort of funky thing, right? And then that updates the representation, and then you back to the residue level representation, and then again you're doing global attention, right? So sort of interleaves this sort of tokenized global attention with sort of atomized local attention. And they say this, and I think it makes sense, is that this is sort of it's a bit of a compromise, right? They're doing this because it's too expensive to do full sort of atomized attention. I don't know if Gemini has kind of like the architecture to be able to do this, on like a full, fully atomized representation. That would be kind of nice. But I think that's kind of that's where the current bottleneck is. And of course, again, the attention here is a lot more expensive than vanilla attention. So that's partly what's driving this. So let me stop here because I want to leave some time for questions. Yeah, that's fine. Just the last thing, I just want to kind of end with this pitch. So with OpenFold, right? So we have this sort of system, right? Like I said, we are building OpenFold 3 now, which is producing AlphaFold 3. But the intent here, and this is a bit of an experiment, I think, in an organization, right? The intent is to kind of build up something which is more of an academic industry consortium, right? With the intent of basically saying, we're doing something of sort of public service. A lot of people are interested in this. Maybe it's the kind of thing which doesn't quite they don't sort of check all the boxes of like what a scientific publication people often want to see in a scientific publication in terms of like new models or new ideas. This is mostly implementation, right? But nonetheless, it's clearly a public service. It's clearly something that a lot of people want, and which directions to pursue and which questions are of interest is also something that we think can be steered, right, by the community in sort of exchange for support, both financial, computational, and so on. And so that's sort of really the idea. And we are obviously going after OpenFold 3, but obviously all these other things as well, which we think are interesting, right? And the hope is that this sort of provides a kind of an alternate mechanism to do this than the kind of the more the conventional academic lab and the more sort of the industrial lab that like say DeepMind And yeah, so I'll end here. Thanks to the support of the sponsors and all the folks who led the work. Particularly, I will call out Jennifer and Nazim, who's the lead engineer, lead scientist in the group, and some of the PhD students in my lab, particularly Christina, Lucas, and Gergo, and Gustav, who led some of the early work on OpenFold and the current work in OpenFold 3. And yeah, I'll stop here. Thanks for your attention.
Yeah, thank you for the great talk. Very interesting. Forgive me one more very naive question. So I'm absolutely not an expert here, but my understanding is that these sort of methods are essentially shortcutting a molecular dynamic simulation, right? I mean, if you had like unlimited compute, you could just kind of run molecular dynamics, and that's actually probably where the training data comes from, right? Or
training data comes from experimental structures.
Oh, okay. All right.
Yeah.
Okay. My question is sort of a lot of your talk, if I understood it correctly, was to kind of really reduce the error quite a bit further, right? I mean, couldn't you just kind of then, do like an AlphaFold prediction and then run a little bit of molecular dynamics on top of it, or is that done in practice at all, or?
Right.
Or the other question would be, could you use the energy, the ground truth energy function that you presumably know, and use that as a guidance signal on top of your data-driven diffusion approach, for example?
Both are very good questions. So for the first question, things like, does MD help? In the case of just proteins, especially monomers, historically it has not. Even prior to AlphaFold, actually, in CASP, there was a refinement category where people just apply MD to predicted structures and see if they can improve them. And generally speaking, it didn't really work. And I think the issue here was just the timescales involved to go past relaxation into sort of a regime where you're actually now finding new conformations that are maybe better than the predicted algorithm, than the ones predicted by the algorithm. I think it just weren't there. Right? There just wasn't enough compute to really get there. So for that, I think, and especially now with the quality of the structures that come out of AlphaFold, I would say, by and large, it's sort of not really needed. I think where it is likely to have a much bigger impact is in the small molecule case, right? Both because because of the fact that these methods are by no means perfect, particularly for new chemistries, things you haven't seen before, and especially if you're trying to say compute physical quantities like binding affinity, right? Methods like free energy perturbation really help you in that case, right? So I think my sense is that in this sort of new realm, physics-based methods, including MD, will be much more useful. But it wouldn't be for the vanilla protein case. It's in these kind of more complicated, small molecule binding or post-translational modifications, things like that. As the second question, so it's always tricky to know how much physics or how much prior information you want to put into the system, right? And I will say, as somebody who who likes to think about physical systems and likes to kind of bring that information into these models, it's been a little bit disappointing in a way what the trajectories look like, right? In the sense that, certainly the progression from pre-AlphaFold 2 to AlphaFold 2 was, fewer priors, just to let the model learn more and more. And with 3, it's even worse in the sense that they don't even have a covariance anymore, right? So it's like that basic thing that we know about the nature of space is not even being baked in, let alone anything about like an energy function. So empirically, the answer seems to be like it hasn't yet helped, or it doesn't help. That I still don't think that means that it won't. And I suspect, in particular, for problems where we are very data poor, that's going to make that will make an impact. Already, we're seeing this with some of the conformational stuff, right? That training on MD data in this case actually seems to be doing something interesting. So I think it will eventually, there will be use cases in areas where this becomes quite important, but it just hasn't happened yet. Is my view. Yeah.
Excuse me. You mentioned in your talk about architecture design choices making your approach very data efficient. My understanding is that as you scale to really large scales, a lot of these architecture restrictions can actually make it harder to train. My understanding is that sort of happened with AlphaFold 3 where they got rid of equivariance and made it the architecture. Can you comment on that as this project moves forward?
Yeah, I think that may well be true. I mean, I should say, in all those cases, we're in the low data regime. Yeah, to be right? In the best case scenario, it's like 100,000 data points, right? So it's all low data regime. I will bring sort of one example that I think supports this view, not in the equivariance case, but something else. So one example I didn't show with OpenFold is we looked at how the structures look, the predicted structures, as the model is training, right? So try to understand a little bit about the training behavior and the kind of the intermediate model states, if you may, right? And what was interesting is the model kind of generates initially these sort of pancake protein, right? Where you can take the 3D structure and essentially kind of flattens it into like a 2D pancake and even like a 1D line. So basically, if you look at how the model is predicting structures, initially it's predicting these like 1D line proteins, and then these sort of 2D pancake proteins, and then finally 3D proteins, but they don't have the right, the kind of the right details, the right atomic detail. So, for instance, right, if we had imposed, and I've done work, I think John here has done work in the past on these kind of protein structure prediction methods where physical priors are imposed, including notions of like steric avoidance, right, that you don't want steric clashes. What this seems to suggest, right, is that at the minimum, if you had introduced that kind of no sterics constraint, it would have dramatically altered the optimization landscape, because the model, as it's training, right, goes through states that are like highly non-physical, and presumably that's the most efficient way for it to learn, right? So that is support to what you're saying. I think the architectural innovations, I will say though, in AlphaFold 2 and 3 and so on, they have not been so much on the physical priors front. It's more, I will say, almost in the like internal communications front, right? It's like, what do we think the model needs to do to be able to communicate to really critical pieces of information that we have some prior on are being important to communicate, right? So how can we design the architecture so that those sort of bottlenecks are sort of streamlined, so it's able to communicate well? And I think it's that. And so I actually, my bet would be is if we had enough compute, an AlphaFold-like architecture, even for like GPT-based models, where you're doing this sort of kind of like an edge transformer, essentially, would actually be even better. But I think the compute is very prohibitive. But with proteins, the token length is sufficiently low that you could throw all that compute at it. So their priors weren't physical. They were really much more about design choices about communications within the network.
I know you had to skip a few slides at the end, so I didn't see what they're about. But I was curious also if you had any impressions on just the role of distillation, cross-distillation, data augmentation.
Right. So it's hard to know without the ablation, which we'll do. My guess will be is that I think it played a role in learning a bit of physics function. Particularly the antibody stuff, right? I think that's actually probably coming from the 40 million magnify structures and so on. One thing I didn't really talk about, so we're building a sort of a single sequence model with like massive self-distillation, like really, really large scale, like 1 billion predictions kind of thing, and we're actually seeing very good performance. So I do think in terms of this kind of question of like, does the implicit physics function get better and better if you do that, right? So from our results, I'm kind of speculating that their gain is also coming from that. Yeah.
Cool, thanks.
Thank you for your talk. I was wondering, with respect to the sort of multimer section of the talk, what exactly was the TCS metric that was being used in, like some of the plots at the beginning, and how do you feel about its like suitability as a metric for success on those like multimeric tasks?
Yeah, so the metrics are always kind of a moving target, and every CASP introduces like a bunch of new metrics because they don't like the previous ones. I actually don't remember the exact definition for ICS for CASP 15. Generally speaking, what it's doing is it's sort of, it's a bit like GTS. So it's sort of counting the fraction of residues that are within a certain kind of angstrom delta of where you want them to be. And in the ICS case, constrained to the interface region. So you're sort of ignoring stuff that's happening elsewhere and really focusing on that interface region. That's generally kind of the flavor. But they vary quite, like I said, like it's always a moving target. Whether they are sufficiently good, if you look at the resulting structures and just kind of like eyeball different like different buckets of ICS versus what the structures look like, I think it's pretty decent. It does seem to kind of differentiate well predicted versus not so well predicted structures. So I think it's fine. None of these are training signals, right? Just to be clear. The training is completely different, right? With AlphaFold 3 is just MSE. So these are all sort of these are just really independent assessment metrics.
Thank you.
I guess we're kind of out of time, but I'm going to sneak in one more. I was wondering if I didn't quite grasp what you had said about when you spoke to Alex Rivas about if you were to scale up. I think you were saying if you scaled up the architecture of ESM, that there was some expectation that something would happen. Could you just instantiate the somethings?
So the scale up is both model size and data. right? Because like ESM2 strain like on like 200 million proteins. We have like 50 billion proteins. Yeah, so orders of magnitude more. I think the intuition here is a bit like with LLMs and like in context learning, right? So there's these sort of phase transitions where it seems like below a certain scale, you're sort of below a certain complexity scale, the model behaves one way, and then suddenly once you get past it, sort of new capabilities emerge that really seem to be in some sense qualitatively different than what had been there before. So I think maybe his view is that currently they're all like POTS model, fancy POTS models, but that as you push that further and further down, as you push perplexity further and further down, it'll extract all of this to extract from POTS-like sort of data or whatever representations, and then it has to do more. It will have to do more. But that right now it's sort of not incentivized to do that because the low-hanging fruit is in those representations. That's his sort of speculation, and I think it's not. I'm seeing sensible to me.
I see. And so, do you think that if he were to do, or someone were to do that, that the that curve where the performance degrades with the depth of the MSA becoming lower, like in particular, do you think it would suddenly become more resilient in that region?
I think so, but the approach we're taking right now is more the massive self-distillation. So we're sort of, at least temporarily, we're kind of giving up on language models for proteins and just like pushing one hot encodings all the way down to structure. But I think so. It's just that my sense is ESM3 is going to be like, the scales are going to be very, very prohibitive for an academic lab to do. We're already pretty stretched in with OpenFold 3, so it would be hard for us to do at least.
Well, thank you for your public service of OpenFold and a fantastic talk. So I guess we'll wrap up. We'll come back at 10:30, and hear a kind of related talk by John, I think. All right.